Welcome to the future.
Welcome to the Muxall Open Internet of Things video blog. I am your host, Michael Crane. In today's video, we're going to look at the PCB layout for version 1 of the Muxall Active IR detector we designed in video 11. We will panelize the PCB for manufacturing by Seeed Studio. Then, we'll see how our PCBs turned out and how well our new IRD works. So let's get started. Alrighty, so I have already designed the layout, the PCB layout for our version 1.0 active infrared detector. Here it is on the left. Here's the schematic on the right. And I figured, there's plenty of videos on how to lay out a board. I'm not doing anything real special. I just basically laid it out similar to the way the OSET board was laid out. Of course, with a few changes. Some of the goals with the PCB layout here is the new Muxall board needs to basically mount exactly like the OSET board. On the right here is the OSET board, and you can see it's got a mounting hole. I just measured it and made it the same size. It's also in the exact same spot. I put the header in the exact same spot. Unfortunately, I flipped it around for some unknown reason in the schematic, and it just translated straight onto the PCB that way. So here on the PCB, you can see that the left side is the output, where on the OSET board, the left side is a ground. And that's bad because this is supposed to be a direct replacement for this OSET board. And so the header, the location of the IR detector and the IR transmitter all need to be pretty much in the exact same spot on the new board as they are on the OSET board. Okay, so let's see, what did I change on this? So the layout is very similar. You can see our 74HC TI NAND gate is pretty much in the same spot. These capacitors right here, all this little stuff doesn't matter. Probably the biggest difference between the layout of our new board and the OSET board here is I moved the blue indicator LED down by the J1 header here. And I did that because I was a little concerned, and it's probably not justified. I doubt LEDs are very monochromatic. It's probably easy for this detector to filter it out. But anyway, I thought it would be better at least away from the infrared detector so it doesn't cause any kind of interference. All right, so another thing I changed is on the OSET board, they have the frequency adjust pod on the left and the distance adjust on the right. On mine, I flipped it around. VR1 is actually for the distance. Let's see, we can look at the schematic here. Yeah, so here we go. VR1 is to dim the IR LED. VR2 is to adjust the frequency. And there was no special reason for me to do it. It kind of made the layout a little easier. I tried to avoid these big runs all the way across the board. You can see here on the bottom, we got a big one going across there. Yeah, so here's the bottom. And you can see this is that one big one. I was trying not to break up this copper pore too much. As you can see, it got a little bit thin. Everything's not coming through this little piece of solder pore right there, because this is basically the ground plane, right? Let's see. That's pretty much it, the layout. I mean, some of these caps have moved around a little bit. I moved them around depending on if they're closer to one pot or the other, just trying to make the traces. I try to get as many traces as I can on the top part and then route on the bottom part last to try to keep the ground plane in as one piece as possible. Yeah, and just looking at this, I kind of stopped the video for a minute and took a look at why I left it like this. I was kind of, and I was looking at it. I was like, well, I could have just popped it up, right here somewhere and brought it over and then popped it back down. That would have left a lot more of the ground plane, the copper pour ground plane, intact on the bottom, right? I mean, I could have made basically this whole section right here part of the ground plane, then just had two little pieces. Anyway, I'm going to fix that in Rev 2. I'll make sure to write that down. Okay, so let's look at the schematic and the layout here, and we'll just go over this real quick. So here's our TI NAND gate, our 74HC, which is this guy right here on the schematic. The infrared receiver, this TSS P4038 mounts right here on U2. The blue LED I already mentioned is down here. The diode, the IR diode or transmitter is right here. And VR1, which is the distance control pot, is on the left over here. And VR2 for the frequency adjust is right here. That's this pot right here. And our new little transistor Q1 is on the left over here, and it's right close to VR1. What is C2? C2. Oh, that's that smoothing cap. It's right here for the power. And of course, the TI the spec says, you really want this cap as close to the VCC pin as possible. So I stuck it basically right next to the chip. Can't get any closer than that. And of course, we already looked at the header, which is this guy down here. It actually fit on here very well. I probably could make this board even smaller, but I'm not going to because it's already pretty small. It's 24 millimeters by 22 millimeters, so that's pretty small. Okay, so as far as the design rules go, there was really nothing that needed extra attention. So the Seed Studio, I'm going to have these manufactured at Seed Studio, and they're $4.90 for 10 PCBs. With these, what's highlighted in green here are their minimums. Yeah, the 0.4 millimeter solder mask down is not a problem. The pin pitch on our TI NAND gate is larger than that. Minimum drill hole size of 0.3 millimeters, not a problem. And our trace space of 6/6 mil is not a problem either. So we should be able to get these boards made pretty cheap. This is 10 boards, 10 PCBs. Here it is. Quantity 10 for $5 is pretty cheap. But so the dimensions of 100 millimeters by 100 millimeters is much larger than our 24 by 22 millimeter PCB, right? So I decided let's panelize it, all right? If you've never done this in dip trace, and I hadn't at this point. Okay, yeah, so you go up here to edit, and then panelizing, and it pulls up this little dialog right here, and you tell it how many columns and rows. And what's nice, it kind of calculates it down here. So as long as we stayed under the 98 millimeter or the 100 millimeters, right? And we also have to include a border. So they're and that's actually, let me pull this up here. Panelization rules. Yeah, so they don't charge any cost for identical designs, meaning as long as I'm doing the same board, I can put as many on there as I can squeeze on there. I to an extent, they do have minimums. So, and we can go look at this. So this put a V-cut line in the outer layer, layer 20 in Eagle, and if possible, make a note beside the V-cut line. I could not do this in dip trace. There is a new version of DipTrace out there. Maybe it'll allow it. I don't know. I haven't downloaded it and tried it, but they want this little note there to say this is where you're supposed to cut. Okay. And so here's the V-cut rules, and so it needs to be greater than 7 centimeters by 7 centimeters. All right, but we're staying under the 10 centimeter because we want the $5 price, right? The subboard size should be greater than 8 millimeters by 8 millimeters. Yep, ours is 24 by 22. And they'll charge you more if it's under 15 millimeters by under 15, but we don't have a problem there. V-cuts can only be straight lines. That makes sense. Edge to edge. The V-cut line must zero pitch between subboards. This just basically means they don't want you to put spaces between all the boards because then they'll have to V-cut, twice as many times, right? Okay, the minimum distance between circuit wire and the V-cut line is 0.4 millimeters. And you can put that in your design rules. I didn't have a problem with it. The thickness of the board must be greater than 1 millimeter. No problem there. Different PCB panelizations. Okay, these are some options. They're telling you what they can do and what they can't do. I can't seem to find it. I found it earlier. Anyway, it's what is the depth and width of the V-cut grooves? Okay, so yeah, this is what I was looking for. So it says the depth of the V-cut groove score is a third of the thickness of the board. So if you want V-cuts, we recommend that you select a thickness greater than, okay, well, that's that. The width of the V-cut line is 0.4 millimeters. Why that is not on their first page, I don't know. It took me forever to find this. Where I put it is when you go to export the PCB into a Gerber, it has the board outline width. And right here, I just popped in 0.4 millimeters. Yeah, so here's the spacing. This is what Seeed Studio doesn't want you to do. And there's also, they need a border. I think it's just top and bottom. I'd have to go back and look. Yeah, so here it is. It says add margin to hold the subboards. The width of the margin should be more than 3 millimeters, right? And they kind of just show a little margin at the top and the bottom here. And yeah, so that's why I put this border on there. I just put it all around it, but they really just need it on the top and the bottom, right? Oh, back to that 0.4 millimeters. So yeah, so that's going to make all the board outlines, the lines 0.4 millimeters wide. You need 0.4 millimeters from the edge of the line to the edge of your copper. That's why they're saying up here that you need an electrical clearance of 0.8 millimeters is required from the center of the V-cut line, right? So this is why I set the board outline to 0.4 millimeters. Okay, enough of that. Okay, so yeah, after that, I just exported the Gerbers, zipped them up, uploaded them into Seeed Studio, and I'm not going to go through showing you that again. I've done it in previous videos. And yeah, so I uploaded our panels, the 82 by 98 millimeter panels. It only costs $4.90 for all 10 panels. And of course, with the shipping and everything, about $23. And they actually showed up in about a week. Actually, I had ordered some the parts from DigiKey, and they both arrived at the same time. Yeah, go figure, huh? So about 24 divided by 120, about 20 cents a board delivered. So that's, yeah, you just can't beat that. That's just great. Okay, and they arrived, and here's a picture of it. Yeah, looks pretty good. You can see all our V-cuts are in line, everything looks real good. And here's the back of it. You can see the logos came out a little bit small. I made a note to fix that in the next rev. But yeah, all the V grooves look good, and actually the boards break apart pretty good. Let me pull up a picture of one. Yeah, here's a picture of one. You can see where the V grooves were. I mean, we're getting a little bit close with some of the silk screen, but the electrical cleared nicely. Yeah, everything looks good. So let's see if we can take a look at the other side. So you can see the clearance around the copper pour on the back. Yeah, this logo business didn't work out too good. I'll fix that in the next rev. As you have probably figured out by now, you find a picture of it. I have already assembled. Yeah, so this is a picture of the assembled board, which similar to the OSET board. Of course, you can see so these are the surface mount pots that I was talking about. These are pretty nice, and they're fairly cheap too. These are about 30 cents, I guess, or 26 cents, something like that. And the reason why the IR transmitter is not on here is because I had a little bit of a problem with this infrared receiver, and I'm going to talk about that here in a second. Actually, this is actually a MOSFET right here. I was kind of testing out the MOSFET. I just bridged this with a 2 ohm resistor and put the 10K in there, and it worked pretty good. And I'm not going to show you the testing. I thought about trying to record some of the testing, but I kind of tinkered around with this thing for several hours because I was having problems with this detector. And let me show you okay, so here's a 38 kilohertz one with the 15K, the 1500 ohm resistors and the transistor, and they both work pretty good. As you can see, I didn't clean them very good, and you can see where I've been poking around with oscilloscope probe. Yeah, so like I was saying, I didn't record any of the testing. I did record the assembly of this board right here, the first assembly, where I actually put the infrared LED on. Yeah, so the reason why I removed the infrared LED off the board and put it off to the side over here, I was having a strange problem that this detector was always detecting the IR LED, and I'm like, turned the distance adjust pot down to minimum. I even changed the frequency way off center, and it just would not go off. So I had to sit there and debug it, and finally I just cut the LED off to see if this thing was actually detecting light or if there was something wrong with it, right? And of course, as soon as I cut it off, this thing quit detecting, and everything was good. So then I just put some wires on the board and moved the infrared LED out here so I could kind of see what was going on with it. And that kind of brings us up to my list of items I found wrong when I was testing. So one of the problems I had when I was assembling this board right here, this is the first board I assembled, is I didn't have a mark. So you can see the PCB right here doesn't show which way around this NAND gate's supposed to be mounted. So what I'm going to do is they've got a couple lines right here marking one side of the NAND gate. I'm just going to update this silk screen or this footprint and just add a double line on this side right here. So I know which way. I could mark pin 1 or something like that, but they don't really have pin 1 marked on the chip, so I'm just going to put a double line. I think that'll be very obvious to anyone looking at it, which way around it goes, right? Another thing I didn't do is I've got VR1 and VR2, but to anyone that is not looking at the schematic, that means absolutely nothing. So I think this is the frequency on the right, distance on the left, so an F and D. Yeah, so ours are flipped on ours, but put an F and D on here so we know which one's frequency and which one's distance. And the other thing that I'm going to probably add is I want to be able to swap this out with the 56K receivers. I'll mark it so you know which way to turn it to get it to the correct frequency. You want to strobe or want to modulate the LED depending on the type of detector you have, okay? And another thing, so on the distance, I'm going to put a plus and a minus. So, you know, if you turn it one way, it's going to increase the distance, or plus, add to the distance, and minus will minus or subtract from the distance. Okay, and like I mentioned earlier, J1 is flipped around. Yeah, so, and you can't really tell, right? Because there's no labels on it either. So I need to add labels. I don't know if I'm going to go with the GVS. S to me is a little bit confusing. Ground and V, I guess you can kind of figure out. I think I'll probably put O right here, but yeah, it's reversed on this, and plus it needs silk screen labels, right? Oh yeah, when I tried mounting this this board in one of the movement mounts, it needed to be, this diode needs to, or this LED needs to shift a little bit to the left. And I thought I measured that pretty good, but it definitely didn't fit. And I mean, you can kind of shove it in there, but, or it didn't look right. So that needs to be fixed. Oh yeah. So when I was testing the frequency adjust pot, which is this guy right here, right? I noticed that I could get down to about 34 kilohertz, which is fine. You know, the 38 kilohertz detector here will pick it up, but I couldn't get all the way to 56. I could only get to about 54 or something, and it did work at 54 kilohertz. I wanted to tweak that a little bit, so you can see I kind of reworked this board a little bit and put a 681 ohm resistor in here, and that gave me a lot more room to adjust the frequency. Now I can go from 59 kilohertz down to 34 kilohertz. So and that's a good range, and I didn't want to stretch the range out too much because there's no way to know what the frequency is on this without labeling it. So it has to be one full turn to get to the 56K side and one full turn to get to the 38K side. Otherwise, you'll have to put an oscilloscope on it, and people probably won't like that too much, right? So another thing is this 500 ohm pot right here is not nearly enough to dim this infrared LED. And my test bed, let me find it here real quick. So my test bed right here, this is a 100K multi-turn pot right here. And I started cranking down on that thing until I could just barely hold my hand over this and it would detect, and then I'd turn a little bit more and it would stop detecting. And when I pulled this thing out and measured the resistance on it, it was like at 22K. And so that 500 ohm resistor, pot right there is not happening. So I'm going to change this out with a 20K pot. And I kind of touched on it earlier about this. I'm going to replace these TSSP 4038 IR receivers and this TSSP 4056 K receiver with these TSOP 438 38K receivers and the TSOP 456K receivers. And you might be asking why that's the case. And they're both the same price. And so here's the TSSP, what we originally had. And I was looking at the specs and I'm like, oh, this is perfect. Presence sensing, shows an IR transmitter, IR detector. You know, I have two different frequencies I can use. Supports the voltage range we're looking for. So the problem is, and I didn't see this when I was specking this thing out is if you come down here, this example for a sensor hardware. This is, I guess, an application note. And this little paragraph right here says there should be no common window in front of the emitter and detector in order to avoid crosstalk via guided light through the window. And I didn't see this. So when I was testing the IR detector, I basically put a piece of IR transparent plastic that you've seen and that goes in the top of the Muxall movement clock that you wave your hand over, right? And it reflects back. Well, that doesn't work. You know, as soon as I put a piece of plastic square over this, it immediately detects. Doesn't matter how much you reduce the transmitter of the IR LED, it detects constantly. And then that's when I found this, and and so I was scratching my head. So then I found these guys right here, this TSOP series. They actually have a lot more parts on this, but you can see the application doesn't look as nice and neat. You know, that first one said exactly what we're going to use it for. I was like, all right, thumbs up, this is it. But the problem is that this TSSP40 here, okay, so here's the TSSP40, here's a TSOP, and it's missing this guy, this automatic gain control circuit. And you wouldn't think much of it, but what that does, and it's hidden down here somewhere again, when a data signal is applied to the product in the presence of a disturbance sensitivity of the receiver is automatically reduced by the automatic gain control to ensure that no spurious pulses are present at the receiver's output. Some examples which are suppressed are DC light, okay, continuous signals at any frequency, and that is the key. What this receiver does is if it detects the 38 or 56 kilohertz and it's a continuous signal, in other words, it's being transmitted through that common window, this will actually adjust the gain control so it will suppress that signal and it won't give you a false detection event, right? So, so anyway, I had to order new parts. So the last thing that was on my list of things to fix is the marking on this diode makes no sense. I didn't even notice it when I added this footprint, but I'm like, okay, what does a line mean? I mean, it means nothing. It's so ambiguous, it means nothing. So I'm going to put a proper arrow on it so everyone knows exactly which direction this diode's supposed to be installed. So when I get the other parts in, I'll make another video and I'll show some testing of the finished product so we can see how it measures up. Yeah, it took me about a day to figure out what was going on with this receiver. It would have been a very boring video. So anyway, that's about it for this video. If you like it, give it a big thumbs up. That helps. And hit the subscribe button. That really helps. If you have any questions or comments, leave them in the comments under the video, and I'll try to answer them the best I can. And I'll see you next time.